So, continuing from the last video, I have now programmed this, and let's try it. It was a bit hard to read that word, but I see that ICR timer A and timer B is actually working. Then I have some unreadable pink stuff there. I remember programming something between pink, red and green. So I have to figure that out. Maybe pink wasn't such a good idea. And now we see we have read latch is actually wrong there, which is a bit strange. So I have to look at that. We have a couple of problems here, so let's have a look at those. At test number 5 first. It says PB6 OSH, that means one shot, and then TGL is toggle. Same for PB7. Then we have a problem on TOD, time of day. The read latch, for some reason the numbers are correct, but somehow the test is failing. The numbers is correct though. I don't know why it's not green. But those rollover things that I talked about in the last video, they are fine. So that's good. And before I forget to say it, I'm using the original chip. So for these one shot and toggle on test number 5, I will have to use some I/O. So I have to look in the code and see which I/O I have to route up to count. So I tried to record this many times, but I didn't get any sense out of it. So something wrong with the comments and everything in the code. So I will just skip test 1 for now and focus on test 2, the toggle. So toggle means that when the timer underflows, it will toggle PB6, and in the datasheet it also says something about if you are driving PB6, then a toggle on timer A, if it's configured to do that anyway, it will override what you are doing on port B here, PB6. So this is for timer A, and for timer B that will be PB7. Now I had a bit complicated code. I think I was trying to run the timer in underflows very fast and then record it in a big loop with some rolling of bits and bit manipulation and stuff. So I ended up changing the code. So here you can see the timer started. It reads counts on with a count input. And in this test we are going to drive that count pin by ourselves, and we are going to read PB6 on PA6, and the reason for that is because here you can see I have connected PB6 and PA6 together and PA into count. Now the reason for doing this here on port A to port B is that in this test we're supposed to have a hardware that PA6, the port A and port B are connected together. So let's continue. So that means we can expect to see PB6 on PA6. So the first thing I do is just store it, because I don't know what PA6 is to begin with. Then we look at what have we loaded into our timer. We have loaded 2 only. So if you count 3 times down, it will underflow. So that's what we're doing here. 1, 2, 3 times. Then we read it again. And I'm reading port A, and I'm just keeping PA6. That's why I'm adding here. So first I store it on parameter 1, then after the underflow I store it on parameter 2. Now I don't have so much space on the screen, so I wanted to print all of this into 1 byte, so therefore I need to move whatever was in parameter 2 down a bit, and then mix parameter 1 and 2 together. So let's have a look at that. what you can see here is that I'm loading parameter 2. I'm moving the bit 4 bits, so PA6 goes down to PA2, or sort of bit 2 anyway. Then I OR that with parameter 1, so we have one in each nibble, sort of. Then I print it. So let's have a look at the screen. Let's just turn on the computer. And there you have it. Actually, it's showing a toggle here because the bit 6 is actually on to begin with, or in parameter 2, and it's off. Well, the bit number 2 anyway is off. So let's see if that was off. That's the one we did move. So if it's the one we did move, it's the one that we store the last. That's after the toggles. It goes from high to low. So that test is actually passing. It's showing red, but I think the reason for that is because we have earlier. So let's mix these two parameters together. Up here we will store it in parameter 1, so that's our result. That's our result, and then we will use that result. So I'm not sure how I'm going to test this. Maybe I'm just going to compare it with 40. So let's compare it with 40, because we know that's correct anyway. Alright, so let's get on with it. It shows completely something else, 3B for some reason, but it turns green though. So yeah. So I think what I'm doing there is actually I'm printing the wrong number, but since it's comparing with the 4.0, it's actually turning green. So it's just the typical thing I'm doing wrong all the time. So here we have toggle. Here we have the mixing of parameter 2 and 1. And I'm loading parameter 1, the mixed value with 40, which we were expecting. Then we are printing 3B. Here you can see 3B. So what we have to do is load parameter 1 before we actually print the hex value. So let's do this over again. There you go, toggle 40. Perfect. What happened to the toggle arm? It's now correct. Must be some of the wiring then. But why is this one different? So I was hitting reset here for a couple of times, and the result is different from time to time. If I hit reset now, take a look at that timer A, no, write latch and read latch down there. Oh, it says 1111 in green, and then it suddenly says something else. There you see, 92. Isn't that weird? So the readback is different from time to time. No idea why. Alright, so I've changed it. So now it's much lower if you get down to write latch and read latch. And that seems to be doing the trick, actually. I think I was a bit too much hopeful, sort of. So with write latch and read latch, because I was setting it to 09 tenths, so but that wasn't working, so I set it to a full second before it rolls over. I'm programming, taking this chip in and out, and then I was thinking, okay, I'm also compiling, then converting the card, and then programming it. So maybe I can take a step less than doing all of that. So but then it hit me. When I tried to make a build event, I didn't get an output, so I couldn't I didn't know how those macros worked, but check it out. If I expand this, and this was a facepalm moment, look, you can actually see what they mean, so there's no problem after all. So we'll fix that. So I will, when I build the program, I will also build the binary file from the CRT files, and just do something like card convert and so on. Does that work great? Now you can see the post-build step, and because of all the errors I had before, that's why it didn't work. So, but it works pretty well. Takes CRT as input and then creates binary. Right, so now we have C7 and C7 on PP7 and PP6 there. Toggle C7. And if you look at the bit pattern, you can see there, it looks kind of like a toggling. So you have 1 1 1, 0 0 0, 1 1, and then it stops because we don't have enough bits there. Right, so if you look at the side, we can see that timer goes from 2 to 1 to 0, and then when it goes back to 2, on the flow it toggles. And it repeats here. So it's 0, 2, 1, and so on. Okay, I made a boatload of a screen recording and not looking forward to adding voiceover. And well, adding voiceover means I have to edit it first. It's like 2 hours of fiddling with semicolons and boring compiler stuff. So, but now I have inserted the FPGA and it's not programmed. And you can see everything is read almost, except that one shot. So now if I program it, let's see what happens. Well, after making this screen recording, what I've added in the code is basically, I can show you the top level here. I added timer B, and I also added the interrupt 0. So one big problem I had was that I had forgotten to add them to the project. Like, they were here, but the file name was empty. So, right, so let's turn it on. Look at the display. It's doing something there. You can see there's a lot of stuff is missing. Like, I think underflows is not working because the top test is default value, then it's underflow. And then 2 underflows, I think, or count input ticks. But you can see other things are working, like test number 2. But test number 3 is a bit different. And then test 4 is different. Test 5 is different. So, and time of day, it's not working properly. That interrupt register thing is totally not working. So I have to debug that. Okay, for this test to work, I need tot, time of day. Actually, I don't need. I need count, and I was having some problems there, so I've cut some traces to borrow some stuff from PB0 and PB1. I don't have to use that for my test, so I add a connector there, such that I can connect RS0. And no, RS2 and 3 to PB0, because I had it on PB6 and PB7, and PB6 and PB7 are special for the timer. So here you can see the repurpose PB0 to RS2, PB1 to RS3. So yeah, so that's the one thing, and then I will need to look at count. I think I've forgotten this one. So that was commented out. So yeah, So I should just go over it again. Oh no, what am I thinking? I haven't even started using port A and B yet. Right, look in the program here. So you see there you have port B, and here's port A. Yeah. Long story short, I've hooked up port A, port B, timer B, port A, port B, interrupt, and still isn't working, so I have repurposed the 7-segment display again for port A so I can see what actually is coming out there. So I'm looking for port A here, port A register and the direction register, but now if I run the computer you can actually see that something is happening there. So let me reset it. So that's the confirmation that it actually is doing something. So, but what I want to do now is to actually read it back using the logic analyzer. So you can see that it's actually writing to the count bits, because I don't know why the test one there at the top, it's not decrementing the counter. And that one is connected to the count. So, and I have a count is the white one, and it is actually connected. So you can see it, but on the screen here, this is my default file for waveforms, which is the program I'm using. And I basically just follow the numbers I have there in that configuration file. So pin number 9 to RS1. Just hooking up the most basic wiring again. So here we have 11 to RS3. And just double check that's correct. You can see there. So that's correct. I can continue if I want to. I don't have to connect everything. But well, I should actually have them. Maybe I will drop RQ and gonna connect that to PA0. So continue. That's 12 on 5.2. 12 is the green one under here. Let's see. There. Alright. So connect that to PA0. We run it, so we'll have to find something to trigger on. So let's turn it on and see. Right. So let's see. There. I think I've captured something. So let's see. This is actually what I want to see, because here I can see that we have a ship select. We have what? It's 2. Okay, so that's data direction for A, which is setting PA0 to output, and therefore it goes to an output here. So that's correct. So that means that earlier we should see a write to, yeah, to PRA, the port register A, which is written to 0, so that's why this line goes low. So that's actually working. Now count isn't working, so why is that not working? I'm not sure how I'm going to debug that. Okay, I see also that it goes up again here. For some reason, I can try and see what. Well, we're writing 1 into the port register A though. Still working, but I have no idea why. Why the count isn't picking up in the timer. You can see those top numbers there. They are still FFFF. Freaking hell, it's working! Look at that. FFD, FFE. So what was wrong? The thing is that in the top layer here, we have a port, which is like the whole ship. And then we have count. And then sometimes we have internal signals for to connect everything together. So that was what I was doing. Here I made a signal called count I, and then on timer A and B I use count I. Now I have removed that. But the thing is, okay, I can use count dash I, but then I do have to also write count left arrow count I, or the other way. So and I hadn't done that, so actually there was a signal that was undefined. But now we are connecting directly to the port of the top layer, or the CIA's STR structure. So I go to the top here, you can see this is the structure for the CIA, and this is the port. It has a count which can be both in or out. In the structure we have a timer A, timer B, and it's declared with a port also, a count. And then if you go further down, you have the instantiations, like here, and then count. So we connect directly to the port. Sometimes we connect via another signal. This is useful if you go between one module to another, like this. Like for example, timer I and the flow will then go on the input of timer B, such that timer B can count underflows of timer A. Well, then this signal is driving that signal on that other port, but count I was just an undefined, so, or it was defined, but it was I don't know. So it's a new day, or shall I say a new night, and yesterday we saw that we got working that count input, which is really great. But we saw also that when there was a forced load, there was a something not working, or it was counting too much down. And in the test number 4, there was a load on a write to the high byte while the timer is running. And now I have looked up in the datasheet, and what happens if you do that is that the timer should not be affected, if I read it correctly. So the timer latch is loaded into the timer on any timer underflow, right? So if you run it in a continuous mode, it will go to 0, 0, and then it will underflow and go back to the timer latch. Or if you run it in one short, as they call it here, then it will reload, but it will stop. And both those testers are correctly working, as you can see on the screen. So, but the one where you do a forced load, which is the second way it can be, or the third way, that doesn't work correctly, because we see that it runs 2 more than the real chip. So, yes. And here is the thing where you write to the high byte of the prescaler. That means the timer latch actually. While the timer is stopped, then it will be reloaded. But if it's running, it's not supposed to affect it, I think. So that's what we see in the real chip also. And for some reason in this test, the real chip and the emulator stops at 82 and you do that write to high byte. But this FPGA implementation stops at 80. So I was thinking to myself, these two tests that are failing, they are kind of similar. Because you can see here, the test 3, the first test is load latches on a forced load. That means that you basically start a timer and you let it underflow and just roll for a while. And then you do the forced load, which is that bit here. And in the other test is load on a write to high byte while running. Then it's going to continue to run, but the latch will actually change. So when it underflows, it will go to that new value you set, but not before it has reached underflow. So for some reason it goes, actually it seems like it counts 2 more down than usual, but it's kind of similar. It's a forced load in some way. So, well, it's not supposed to force load anyway, so we can look at the one where it does a forced load. What are we doing in the code? So let's have a look in the code what we do. I'm not sure where, but we're going to look in the timer A code anyway. So we can look at how it starts, and we have a timer process. So this is, yeah, it's a bit hard to read when I double click like that. So you can see it has a reset, and I think this code is written a bit weird. I think it's supposed to look like this. But anyway, we have a reset, then we have a serial load. Both of these are asynchronous. Doesn't have to mean it. Could be a reason why it's not working. Actually, when I come to think of it, this might be the reason. Anyway, so if we get a load signal, we can see where that comes from. Then we will load the timer. Then you have the actual counting that's happening here, as you can see. Take the timer value and we do some VHDL trickery to actually make the calculation. So we calculate it with an unsigned number and then we convert it back to standard logic vector, which is the type that is used for the port, I think, I'm not sure. So if it has started, the CRA register bit, this bit 0, which is this one, you can see it here. It's bit 0 and then 1, 2, 3, 4, 5, 6, 7. If that one is high, then it's running. And then basically, yeah, then it's running. And then if we have an in mode, so what is in mode? That is if it's running from count pulses or from system clock. So if it's system clock, that means that in mode is 0. Then it runs for every rising edge of phi. And if it's not, then it will look for a rising edge on count sync. So I changed this code a bit since I showed you last time. But it's basically the same, it's just that I have delayed this signal by 1. So that can actually affect it somehow, this delay thing. So we can quickly look at count sync. You must remember that the count pin can be asynchronous. Most likely is asynchronous. There you can see, so count sync basically takes the count signal and then puts it into count sync. So since we have this inside a process with a rising edge of phi 2, so this signal is now synchronized with phi 2. And then I take that signal again into count sync 2. But since it's in the same process, this signal will actually be 1 pulse later than this one. So therefore I can see, okay, if a count goes up, first this one goes up, and one pulse later this one goes up synchronously to phi 2, and that's what I'm actually looking for here. So if count sync 2 is still a 0, and then count is now going up, then we know it's actually going up. So we have a sort of a edge detect on that asynchronous signal there, which is now synchronized. So that's it. But nothing here shows you how to do a forced load. And let's see, we can do a load here. That's asynchronous to the clock. That might be the reason why this happens. Let's see where that serial load happens anyway. So we have another process here which is listening to the clock and reset. It can reset the register. Okay, so this one is for writing to the register from the computer. So if we do a write from the computer to register E, which is the control register A, we set that bit. We saw that in the code. We did so, actually. Sorry, here. Can you still see it? It's a bit bright. Sorry for that. And test 4. No, there's test 3, test 1. Okay. So we see here we have that one. So you write 1 into timer control, which is CRA in this case. And 1 will be start, and it will be load. So therefore low goes high, and then in the next falling edge of phi 2, it will go back to 0. So this is a signal that is only for one half cycle, or one cycle. Another problem maybe is because we're looking only at the falling edge. Maybe we should run the timer only at falling edges. I don't know really. We have to figure this out. So, and remember that other thing, that was failing was that when you load the high byte, then the timer is only updated if you do that on a when the timer has stopped, and that's what I'm doing here. So this is updating TA high, and we are setting CRA load to 1 if we actually do this writing here now. So let's look at that load thing. We should have simulated it, then we probably would have seen it right away what the difference was. One thing I'm seeing here is that this one is not synchronous at all. So instead of thinking so much about it, let's try just trial and error. Just put it in this if-else-if statement. So let's just try that. Right. Dun-dun-dun. Well, now it says A4 and A2. It's actually exactly the same as before. Alright, so managed to get the numbers up by 1. I'll explain, not exactly, but the only thing I changed was this from rising to falling. That's a good thing, because then it's everything is at falling. Yeah, because these two processes, they are in sync. And the problem I have now is when it comes to 0, it raises a flag. And the problem with that is that when it's actually underflowing, the flag is high. The problem is that whatever's happening in the next process will happen a cycle later. So okay, so it reads underflow high here, and then it will stop. But it will stop too late. So what happens? Now it actually says in test 3 there, you see 0101. Before I made the changes that I didn't show you yet, it says 0100. And you can see the numbers to the left, they are 85 and 81. They are actually one closer to the real number now. So to fix this, instead of waiting for underflow flag to be 1, which is when it's actually underflow, we can say timer A equals 0, like this. I think now we need double quotes. So there you go. So if I run this now, you will get what I showed you up there. So because then we are one cycle earlier. So if it sees that, you can damn straight be sure that in the next cycle it's an underflow, then it stops. But what we had was we looked for the underflow, and then in the cycle after that we will stop. So that's why it goes too far. However, the other test, how am I going to fix that? Not sure yet. So I have to think about that.